registro. Riprovata? Non l'ho mai provato. Oh, okay. I actually keep faith to my promise. I produced some material about last lesson, some more sorted material for last lesson, which is here. It's called electroarima. I'll just review this very quickly because then we go to our new topic. Okay, so I tried to synthesize everything we did last lesson and organize it in this ARC Markdown. I tried to produce even better plots using ggplot, just because when you produce something to be, I don't know, compiled into a HTML file or into a PDF, I like also that it looks good. Anyway, so here are all the passages we did last time, moving from the hourly time series to 24-hour daily time series, and then back, because we used that form also to rebuild, for example, the missing hour number 24 for the daylight saving changing times. And yeah, this is the general plot. Okay, here's the variance stabilizing transform. We did something similar. I don't remember if we applied that to every week or ops, scusate. E poi venite di persona e non riuscite, dovete lo stesso guardare. C'è pure lo schermo. Okay. È uscito giusto? No, è uscito sbagliato. Okay. So, yeah, I did the same thing using also slightly different ARC scripts. In this script, I used much more the deployer or the tidyverse word. Indeed, I didn't use the tapply function, for example, to produce this means and standard deviations plot, but I used the SQL-like tidyverse approach. So I use mutate to create the week of the year, so a number going from 1 to 52. And then I group by the week, and I summarize by computing means and standard deviations, and then I do the ggplot of that. And I also use linear regression to enhance, so to stress the fact that there is a good linear relationship. So this is still R. This is probably more readable, or anyway, more modern. This tidyverse approach is much more popular in later times. And actually, it's much more readable, I would say. And here, for example, I figured out a plot so that you could see very clearly the two different seasonalities that we have in this data. So the every 24 hour, but also the day of the week in some day, in some kind, yeah, the day of the week effect, okay? Particularly Saturday and Sundays. Here I also did something more for exploring the within-year seasonality in this case. I think this is, I forgot. Okay, this is just hour number 12. Weekday number 4, which is a Wednesday. So this is just one type of day, 1 hour. And I plot that over all the years, but just with respect to the number of the week within the year. Because this plot makes very clear that there is a within year seasonal pattern. So something we didn't do during the lesson, but which is actually very useful to do. There is actually a seasonal plot. If you look at the book by Heinemann, this online book, he uses a lot a package called Fable, because it's made by his scholars or his students, and I think there's like a seasonal plot that kind of do the same thing here. Okay, here it's been more handcrafted, but there's probably some functions that do that. And it's nice because we see, of course, what we already noticed. So the minimum in August, the minimum during the winter vacations, but then you see these negative spikes in their Easter vacations. They're very strong, actually, almost as strong, and something more strong than the August effect. Of course, it depends probably when other holidays are close to Easter. Of course, if Easter is close to other holidays, then the probability that a lot of people is going on vacation is higher than if it is Easter is kind of isolated from other holidays. And then I didn't expect this, but on some years, not always, probably there are 2 years in which, again, there was some weekend close to the 1st of November holidays, and we also see sometimes these negative spikes, which is interesting. I mean, of course, I didn't model this very specific spikes, but one has to reason about that and find ways to provide that information to the model. So some reasoning, so some real neural network, human neural network reasoning about what's the rationality behind if going everybody on vacation or not. For example, for many years there was no vacations, not striking vacations, but for 2 years there were incredible quantity of vacations for the people. So anyway. And of course, there's the COVID here, the COVID effect, just on year 2020. This is the same thing done for Sunday. And of course, here we don't see all those negative spikes because Sunday it's anyway holiday. So all these extreme negative spikes disappear if I just look at the Sundays. Okay. And then, of course, this actually we already saw during the lesson how to find out also these many seasonal patterns by looking at autocorrelation functions. Again, here I use the ggplot version, which is in the I think it's in the forecast package of the ACF function. Yeah, and I put some breaks. You see this vertical line I put on multiple of 24. Okay. And again, we see the spike every 24 observation, and we see the spike going up back after 168 logs because of the week day of the week effect. This is the same after taking the seasonal difference with respect to the day before. So, and now the spikes about the weeks are even clearer. You see, I put again the number here, the numbers in multiple of 168. And finally, this is, if I take a difference on 168 observation, I kind of get rid both of the within year seasonality and the within week seasonality. And so I enhance the dependence with respect to the previous year. So this is just about 1 year, okay? So there are just a few different ways that I put in this HTML to find out if there are seasonal patterns and what kind of seasonal patterns are there and how strong they are. And here we clearly have 3, and they're all relatively strong. And this is another thing that I didn't show last time. We just commented on that, but then I had more time to prepare this, so I wanted to show you how the day of the week and the period of the year affect the shape of the consumption within 1 day. So this is the hourly pattern. So every 24 hours, just like it looks like, I think on the average, did I take? Yeah, I took the average somewhere. Yeah, here. So I took the average. So I picked up. So first I generated the name of the day, the month, and the year, and then I selected just 1 year. For example, 2018. I selected just 2 days, one Sunday and one Wednesday. So 1 day which is in the middle of the working week and the Sunday. And then I picked just the month January and July. So I just picked very few observations. And then I grouped by weekday, month, and hour, where the weekday is one of these 2, the month is one of these 2, and now the hour are all the 24 hours. And then I take the means of the load, which it becomes the mean load for that day and for that month. And what is nice to see here is that this is 24 hours. This is the, this up here is Wednesday. So the dotted line is Wednesday. And you see the consumption is higher, but also the pattern is not completely different, but it's kind of different, okay? It's not just a reproportion, or it's not just this one which is moved up. It's also, the shape is a little bit different. Not completely, but a little bit different. And then if we look at the 2 periods of the year, January, of course, in winter, and July in summer, and in that case, we see the 2 different colors, and we see the shape is very different in winter and in summer. Okay, so this figure is just this plot is just to show you how these 3 seasonalities are interacting. So how the within day shape is affected by the day of the week and the period of the year. So that's what makes this time series tricky to model, okay? And that's why probably working on 24 different time series makes the problem less relevant as if I worked on the hourly time series. Because if I work on 24 different models for every hour, I don't have to take care of this explicitly, at least, of these interactions between all the seasonalities, okay? That's why that model is much easier. So I made a model for daily data and hourly data. So of course I generated the same amount of sinusoids. In both cases, I just used 15 sinusoids as we did in class last time. You see, I generate both for the day. So when you see 24, it means daily data. So 24 models for daily data. And you see, I just built the frequencies for the first 15 sinusoids with base frequency 365.25 days. But then I do exactly the same thing, but changing the base frequency, of course, which is now 8,766 for the hourly data. So these are the same 15 sinusoids, but observed either on daily frequency or on hourly frequency, okay? And I build this of course, cosine and sine regressors matrix. Then this is just what we did last time. I built the holidays from scratch. So I took note of all these holidays, and I prepared a data set that checks if every day belongs to any one of those holidays. And then I add the Easter Monday, which is actually already contained into the time date package here. There are also other packages. I just picked the one that I had. But anyway, this we actually saw during the lesson, so I don't spend much time here. And here I'm adding just a demi variable. So I'm building a new matrix where I have the old matrix just with the sinusoids, either for the daily time series or the hourly time series. And I check if the date belongs to the list of holidays that I just built, okay? So this results in the creation of a 0, 1. So true, false would get turns into 0, 1 because this is a numeric matrix, okay? And then what I do here, okay, then I created also here very clearly also the case in which the holiday is either on Sunday, so 1 is actually Sunday, or Saturdays, which is day number 7, okay? So I just take the product of the dummy, which I already built, and this other dummy that signals the presence of Sunday or Saturday, okay? And so now I have all the regressors that I wanted, and I can go with modeling. So this is a more short-range autocorrelation function, a partial autocorrelation function. For example, here, I think I just put 3 delays for the autoregressive part, and then seasonal MA part, indeed. Actually, I put also a seasonal autoregressive part. This model, I think, is very close to the last one we did during lesson. Here are all the regressor, and just keeping the last 30 days off so we can predict. Okay, I'm working on 5 p.m. as we did, I think, during the class. I think I did the same for all the 24 hours. So I just used the same model, so the same ARIMA 300111 model for all the 24 hours. So I estimated 24 different models for, I mean, same ARIMA models, but of course, different coefficients. Well, this is okay, I did something also to have the t-ration and the p-value. So this broom is just a package to make things more tidy. Again, as I was building the R markdown, so I tried to make things look better. So this broom tidy takes the output of, I don't know, a regression, a ARIMA model, whatever, and makes a table or data frame out of it, okay? And then I added, of course, this create estimate and standard error. It doesn't have any t-ration in p-value, but as you see, I added here the t-ratio, which is just the estimate divided by the standard error, which are already contained in this data set, on data frame. And then this is a simple way to build the p-value, a symmetric p-value, okay? Based on the t-ration and based on the asymptotic normality that we use. And of course, then I print a table with 4 digits, and this is it. So you can actually see there are actually some regressors we could throw away. I didn't do that because anyway, we have many observations, but we could throw away some of the sinusoids and some of the, some of the sinusoid, I would say. So the holidays are present. So this is exactly the same thing we obtained last time. So 33% less consumption on holiday, but when holiday are on Sunday, I go back almost to the same value as if there are not holidays. And on Saturday, it's mixed. I go back a little bit, but not completely. So there's still a minus 10% when the consumption is on Saturday holidays. And then I checked for the white noisiness, I would say, of the residuals, and they're okay. I mean, there are a couple of delays that are outside of the bands, but anyway, there are small numbers. Okay, there are very small correlations. I know something. It looks like either I checked something wrong last time. I don't know why. It's much better today. I'm not checking the within year seasonality. Maybe I was not happy with that, I think. So here I'm not checking. I'm just checking the short run and the 7 days seasonalities. I mean, there is still some here. Look at that. And here as well. But we did everything we could, so I won't be able to kill this. And anyway, if you look at the numbers, they're very small correlations. So it's like 0.05 here. So it's really not that relevant. And this is the partial autocorrelation. We're in the same scale, so it's not that bad. So this is just in R, you should get acquainted with the apply family of function because it makes things. I mean, they're just like for loops, okay? But they're more readable, and in some cases they're also faster. The bare apply functions, they're not faster. If you look at the apply function, it contains a for loop, so it cannot be faster than a for loop that we built. But the everything that it has to do with list, for example, lapply or sapply. Sapply is just the lapply that tries to simplify the results. Okay, so lapply, you apply a function to every entry of a list, and the output is a list with the results. Sapply tries to see if this new list that you created could be simplified into a matrix, into an array, or even a vector if it's just a scalar. So, and these two functions, they could be quicker than for loops because they're not for loops inside the function. They're more basic, so they're closer to the machine. So what I did here is I did lapply. So I'm using all the time series excluding the first one because the first one is just the date. So I'm taking the data frame, excluding the date. So I have the 24 hours. Of course, I'm keeping just the last 30 observations to predict. And remember that for an lapply function, a data frame is just like a list. And it runs over each variable, okay? You can see the data frame is a special kind of a list. So this is working by every hour time series. So this is building 24 models. You see, so every time one single time series is passed, and I just apply the same identical model. And so models will contain a list with 24 estimations of the ARIMA models, okay? And then what I do here, I just wanted to produce forecasts for the last 30 days, okay? And what I did is I used the sapply function. As I told you, sapply is just like lapply, but it simplifies into a matrix or something like a matrix or array if it can. And so I passed the models, and the function received the model and just apply the function forecast, of course, with a regressor that now is the tail, so the last 30 observation of x24, and takes the mean, which is just let's say the time series of the 30 prediction we're producing, because we are predicting, so we're passing 30 new regressors observations. So we are producing from one step ahead prediction to 30 steps ahead prediction, okay? And of course, this can be simplified. Indeed, this is a matrix where you have the 30 times in the rows, and you have 24 columns where you have the 24 models, okay? And finally, I want to compare, I want to transform this 24 daily prediction into like an hourly prediction, okay? So again, what I do, here I'm comparing. So this is just, I'm taking the data, I'm just selecting the last 30 days. Remember that this is the hourly time series, so 30 days are 30 times 24 observations. Then I create a new variable, which is called a forecast, and I just extract from here the forecast produced by here. Why do I do this? Okay. We have to transform this. We have like our prediction are like first day of prediction on the rows, and then first hour, second hour, third hour, 24th hour. Okay. So in R, a matrix is like taking a long vector and just cutting every I don't know. It depends on how many rows you have, but cutting that vector. So what I did, I first transposed the matrix. Now we have like the hours in the rows and the days in the columns. Then if I transform that into vector, I'm just producing the hourly time series of the forecast, just because it just stacks by column, so column under column. So that's an easy trick to, and of course, then I transformed it as in a numeric vector, so as numeric. So the hourly forecasts are very simple to build, or they're just built this way, okay? And so what I do here, like pivot longer. Yeah, this is just because ggplot wants, so ggplot it wants data to be tidy, so I have to build like a really long data set with the original time series and with the name, I think, load as a new field, and then below the forecast and the name forecast as a new field. So that's why there's this step pivot longer, because I have to make just one long column with the loads, and some of the loads will be real, some will be forecast, and there will be a new column called series that tell us if it's forecast or load, and the value will contain both. Well, this is just because that's the way how ggplot works. Okay. And so this is the comparison of the forecast, the red ones, and the load. And they are very close. So actually, it's not bad what we're doing. I mean, the load is not difficult to predict because it's very regular, but I would say we're doing a good job, okay? And then what I did is I built a model for the hourly time series. So again, we already saw all of these things. So I estimated actually the same model. At the end of the day, I applied the same model, but with a period of 24. Now the seasonality is not 7 days, but it's 1 day, okay? But all the rest is the same, okay? And I'm keeping out exactly 30 days of hourly observations, okay? What? We just to compare it because I produced 30 days of forecast with the other model, so I want to produce 30 days of forecast also with this model, so we can compare which model is working better. Okay? And actually, I built 2 models. Indeed, so this is a model where the period of the seasonal part of the ORIMA model is 24, but then I also built another model here, where the seasonal period is 168. So we did the same thing during the lesson, so it's nothing new with respect to what we did last time during the lesson. Here, so I call this mod S168, and you see now the period for the seasonal difference, the seasonal MA, and so on, it's 168. So the same hour, but 1 week ago, not 1 day ago, but 1 week ago. And actually, it's the same model, almost the same model. Yes, there is a 0 anyway. And I did the same thing. So again, there are some things you can throw away. For example, this cos 1 doesn't seem to be there. But anyway, I didn't throw any regressor away. And of course, the effect of holiday is smaller because it's for 1 single day. Okay. And so in some way, in order to obtain the effect on 1 day, you have to multiply this by 24. Okay. So it would be in 1 day, the holiday have a minus 2% effect. But anyway, and here I produce a comparison for all 3 forecasts. So the daily forecast, the hourly with the 24 period seasonality, and the hourly model with 168 period seasonality. And I think I added also something for the day of the week. The other one. Yeah, you see in this model, I actually added a dummy for Sunday and a dummy for Saturday, which actually didn't have any. Yeah, this is significant, but this is not significant. And the strange thing is it's positive. I mean, this is crazy. Anyway, let's check the forecasts, and they're here. So the daily model we already saw, it's good. The real one are the purple one. Okay. Model H2 is good. Model H2 is the one based on 168 seasonal period, right? Yes. And instead, the other one, something went wrong because it's really bad. In some way, there's also some trend, negative trend, which is particularly strange. I mean, I see now there is some problem with also model 2, so H2 has some problems here. If you look at these days, I don't know why. I didn't notice that this should be fixed in some way. You see, there are a couple of days where we have, for some reason, some drops. It shouldn't be there. And indeed, I produced also some summaries, which are here. So I produced the root mean square error for the three models and the mean absolute percentage error for the three models. Of course, the model based on daily observations is the best one. It's like 2% on the average of errors. This is 5%. This is 7%. It's going. Of course, it's 2% on the average because usually, of course, short range forecasts are much better than long range forecasts. Okay, so that 2% is an average. Here would be probably 1%, and here would be maybe 4%. You can check that, but okay. As I told you, you have always to distinguish between like one step ahead prediction from k steps ahead prediction. And keep in mind that difference because especially when you will be working with machine learning models, sometimes you will do the training and the evaluation sets, and the evaluation you will be often be doing using one step ahead prediction errors, which doesn't really, especially for machine learning model, which is not always a good indicator if the model is good also for long range forecasting. Okay, you should keep that in mind, and you should also do the cross validation or whatever the evaluation of your model based on real one step through, I don't know, each step ahead forecast. Okay? That makes a big difference. Of course, I mean, it depends on what's your interest in forecasting. If you're interested in very short range forecasting, then long range forecasting is not in your target. But anyway, keep in mind there's a difference between these objects. Okay, that was it. Yeah, I probably want to check what's going on with H2 here in these 2 days. Maybe it's something that happened in the last available data, and it's being reproduced every time. Well, here, yeah, I have to check. I didn't notice that, but of course, this is something that should be fixed before using this model. It's probably something that happened here in the last data, and I'm just missing it. Okay, that was it. So that was the last thing we said about ARIMA modeling, unless you have questions or unless we do some reviews at the end of the course before the examinations. So do you have some question about this? But anyway, if you have question also later, it's not a problem to go sometime back to these lessons. Anyway, many of the things here, especially how we treat seasonalities, we will be using again. So some part of this is not finished here. Actually, we will be using it maybe in a different form, but also in the unobserved component models, which is the thing so that we're going to treat in this part of the course. So I usually start with the components, but now I will start from the state space form. It's probably better because so you understand why we want to write the components in a certain way. So okay, so check on your feet. what's the state space form? It's a way to write many different time series models, and not only time series models, but they are always time series. And it's made by two sets of equations. So let's start from the so-called measurement or observation equation. So we have and then we also or measurement equation, whatever. We suppose we have one time series, but actually we can also reason already with a multivariate time series, so a vector of time series. It doesn't change much. Actually, for example, up to now we've just dealt with univariate models. So we were predicting one time series at a time. Okay, we could have also time series as regressors, but we are predicting just one time series at a time. Of course, the ARIMA models could be generalized to have vectors of time series. So instead of predicting just one time series at a time, I predict a whole vector of time series. Is that useful? Yeah, it can be very useful because sometimes you have that the past of the other time series are helping also to predict the future of the other time series, okay? So there's kind of dynamic interaction between the time series. And these models are called VARMA model or VARIMA model. There are also some complication because there's also the integration problem becomes also a so-called co-integration problem. So there's something different than just not taking a difference or taking a difference. There's something in between these things. It's not by default part of this lesson, so I'm just mentioning them. And I don't think we will say anything about that. But keep in mind, if you have like 3-4 time series to predict and they relate to each other, for example, if you go in macroeconomics, usually you want to predict, I don't know, GDP together with unemployment, together with inflation, together with, I don't know, the interest rates and so on. So you want to predict like a vector of time series based on the past of that vector of time series. And actually, economists are usually interested in understanding what happens if I shock this variable on the other variables. So that's the kind of things usually economists do with this VARMA, or they usually just use the VAR models because they're simpler. But for pure forecasting, sometimes even a univariate model can even beat the multivariate model because it's less parameterized. But anyway, what I wanted to say is let's just suppose also for the generality of the state space form that Y is a vector of time. And in a state space model, we have, I always forget what letters I'm using for the constants, but anyway, we don't have it in the software we're going to use. I'll just call it CT, maybe it's DT, I don't know. So this may be just a vector of known numbers. I mean, we will not have that anyway later. The important thing is here, we have a matrix that multiplies a vector we will call alpha. And then we have some noise, some white noise. So usually in this vector alpha, we will have our so-called unobserved components. For example, we will have a process that takes care of the trend. We will have a process that takes care of one of more or more seasonalities. We will have regressors or regressor coefficients actually. So we may have in the alpha many processes that usually are defining the component we want to model. and they cannot be directly observed, but we observe the alphas only through the observation YT. And the matrix zeta is just either selecting, in many cases, it's just a selection matrix, selecting which components should be given to which time series. Or just from many components, we will see that some components are just used to build the other components, but they are not interesting by themselves. So in many cases, zeta will be 0 and 1, selecting some of the components that are in the alpha vector. Sometimes in zeta, there could be also other things, for example, regressors. Indeed, zeta could be also time varying. So I put also a T here. It doesn't have to be time varying, but it can be time varying, and here as well. This could be just like a vector constant, like intercepts, for example, something like that. And it could be time varying in a known way, okay? Not in an endogenous way, but in a known, already known way at time t. The same is true for zeta t. So it's a matrix. It can be time invariant, or it can change in time. And this is let's say, a white noise with variance or covariance matrix, because it's also a vector. H, and also this can change in time. It doesn't have to, but it can change in time. And this is the observation equation, because we observe the y's, we don't observe the alpha, and in this equation we say, okay, the y's are some linear transformation of this alpha, maybe with some noise. Okay. This is like the signal we're interested in, and this is some noise on the signal. What about the other equation? The other equation is called the transition equation, or the state equation, because this is called the state vector. This is called the state vector. And the state equation or transition equation is it is actually a vector autoregression of order 1. What does that mean? I'm already using almost, again here, we could also have the vector of constant here, time varying or not. And I'm already using the form that we have in our class package we will be using in R. The only thing that is not present in the class package are these two things here. So this we will not have, and this we will not have. Actually, they're not strictly necessary. We can do without in some way. But anyway, the interesting thing, this is like, you see, it's like a vector autoregressive process, so VAR, VAR, over the one. And this is like the rule. So this is a vector, this is a vector, and this is a matrix, and this is a vector. Okay, now I'll explain you why I put this R matrix. As a starting point, you could think there is no R matrix. Okay. So this is like a transition equation. It tells us how the components evolve over time. Okay. So here we will be defining the process, how the unobserved components, so the trend, how the seasonality, how other components, the business cycle, for example, how they evolve over time. And then we have an equation that relates the observable time series to the unobservable component or state vector that we want to put, okay? Eta is again also a white noise sequence. Again, the matrix we will call Q, and it can, but it doesn't have to change over time. And also the matrix T can, but doesn't have to change over time. Okay? So where I put a parenthesis, most of the time they are not time varying, but they could be time varying. So as you see, this is like a vector autoregressive process. This is the shock, so the white noise. And why do we have this R here? Because when we use the state space form in many of these equations, here there are many equations, so it's a vector equation. There will be just identity, so there will be no noise. Okay, so instead of defining a noise with variance 0, a white noise with variance 0 is something that is always 0. Okay, so instead of in some software, you go with that. You say, okay, we don't assume there is this matrix. We have this eta vector. If some of these entries are always 0, I just define their variance to be 0. Okay. Or, as in the software we are going to use, we can define only proper shocks, so proper white noise. They're not always 0. And then use this matrix to assign each of these white noise to the right equation. So it's just a way to avoid to have like, how do you call them? Degenerate random variables. A degenerate random variable is a random variable which is not random. So this is just a way to avoid that we use degenerate random variables. So if we have like 3 shocks that drive 5 equations, this would be 3 times a vector of 3 dimensions. This will be like 5 dimensions, and this will be 5 times 3, which is, we'll be selecting which one of this noise goes to which one of these 5 equations. Okay, it will be clear, and we'll be doing a lot of examples. Why is this form? I mean, this form doesn't look to be so complicated, so general, but actually most of linear model have this form. You can put in this form. For example, the ARIMA models, you can put in this form. Yep. What kind of what? Yeah, it depends. As I mentioned, you can have a so-called time invariant state space. The time invariant state space, all the things that I put in parentheses, they don't exist. And time invariant state space has special properties. For example, ARIMA models are time invariant state space. Special case of time invariant state space. Sometimes you have just 1 or 2 of them in time invariant. I will give you an example of time invariant zeta, for example, very quickly. Or sometimes you want just the variance. Sometimes you see the variance is changing over time. In some way, you want to let that also happen in the model. I always think of economic examples because I work a lot with economists. For example, there is a period of time in US that is called the Great Moderation, in which much more macroeconomic times here, that's about in the 80s, it happens in the middle of the 80s, where the central bank changes their policy, and actually inflation, but also GDP, all these macro variables, they start being less variable, so less volatile, okay? In that case, you could like define a variance for before and after the year of great moderation. So you have different values, and it's good to give that information to the model, because of course the estimate will be better, the forecast errors will be more accurate, and so on. So there are good reasons sometimes to have a time varying matrices. R is very rare that you need to make that change. I mean, you could also model a change in the variance by changing R, because if R changes, the variance of it changes. But usually R is just 0 ones. It selects just some of the variance and it gives to some of the equations. And zeta, yeah, sometimes it's just 0 ones. For example, in our pure unobserved component models, there will be just 0 and 1. But for example, I'll give a straight example where zeta is actually a matrix that contains regressors. In that case, if you have regressors in the matrix zeta, then you change the f to t. Okay. This is not finished yet. Still, there are some, well, there's a couple of hypotheses. For now on, we will be assuming that epsilon and eta are not correlated with each other. It's not compulsory. If you, for example, look at in my book, I don't assume that they're uncorrelated. You can have them correlated. But since the software, most of the time, software assume that uncorrelated, because it makes things yeah, the formulas get a little bit easier if you have no correlation here, and in some way, even this white noise here, you could move it here. So it's really not a great or a bad assumption, assuming that these are uncorrelated, because if you want correlated noises, you put them here, you eliminate this, and you just play around with the matrices. The nice thing about the state space form is that it's not unique. You can represent the same processes in many different ways. Sometimes, for example, more in engineering literature, these are important because they're like inputs you put into the system to shock. If you go into engineering, of course, engineering things, noises are less important because engineering is all about deterministic things. But then they're important, the input that you put into the system. It's like if I put, I don't know, that quantity of gas per every minute, my turbine is going to produce that kind of energy, okay? And of course, there is a reaction with some delay, so you have to model that using this equation. So we, as statisticians, as forecasters, we put much more emphasis on the fact that we have random noises here. Engineers, they put more interest in that part. But the reaction, you see, is the same. I mean, either if you have an unobservable shock here or a fixed shock here, I mean, the system reacts the same. Okay? For example, just to give you an example on where everybody of you is using a state space form, and of course the related algorithms. The more famous of the ones is the Kalman filter. When you use your GPS, there's a Kalman filter, so something in state space form. And why? So this observation is where the satellite are seeing you, okay? So if you have the telephone maybe catches at least 3 satellite signals and determine where you are, but it's very imprecise, okay? I think the GPS is a precision. If you stay in a point and do not move, I think the precision could be as worse as 20 meters. Okay, so it's not very precise. Here we have the data, but the data are very noisy. And here we have the real position. So alpha would contain maybe the the two coordinates on the Earth where we are. Okay, so this is the real position, and these are the two coordinates observed with noise because of the noisy effect of the GPS. Okay. The nice thing is that when we start moving, we also have some kind of law of motion, because in some way we can say, okay, we were at time t, we were at that point, and if we're going into a certain direction, a certain speed, I can build a t that produces a prediction where we will be in the next time. Okay. So if t is in the seconds, for example, suppose that we already know where we were, at what speed we're going, then we can produce, just using linear combination like this, the point where we will be in 1 second. Okay. So this is the law of motion. And in that case, we even don't have much of a shock. But anyway, this is the law of motion. And this will just select the two coordinates and say, okay, the two coordinates get noisy because of the epsilon, and I observe y. And so what the common filter we will see is doing is trying to estimate the real alpha by exploiting both the observations that we have, but also the law of motion, because there must be coherence between these two things. I mean, if I'm moving, I don't know, 1 meter in a second, and the noise is about 20 meters, this is telling me, okay, maybe I record you now here, and now I record you 20 meters apart. But that's impossible, because the law of motion is telling me I'm moving at 1 meter per second, so I cannot be in a second 20 meters away. Okay, so these two information together are, we will see how are used to estimate the new, so the point where I am now, so the alpha at time t, but also the prediction where I will be. You had a question? Mm-hmm. Yeah. Right. Yeah. I mean, once you have a point where you already have a prediction for the next point. And if it's linear, so actually you can get t plus h prediction without problem. You just apply t many times. Yeah, of course, probably in alpha, I will have not just the position, I will have the position and also the speed. Right. And of course, here you will be selecting just the position. But we will see, we will be working with something. Of course, it would be not have two coordinate points, we will just have one, but we will work with something similar that we'll try also to measure the velocity we're using to move. Okay. And the nice thing, if you think this object here, actually the common filter, as I showed you, is the algorithm that while observing yt, it estimates the alpha t. This thing here was published, I think, back in 66, 67. And it was found so useful by the team that was working on the Apollo project for going to the moon. But actually, the Apollo 11 that went, it was the Apollo 11 that went on the moon, actually had a common filter inside. Of course, the computer was very rudimental. It was not. It's very close to sorry, 1 million of the power we have here. But in order to govern the moving of the spaceship, the common filter was implemented already in the 69 Apollo 11 going to the moon. Okay. Okay, I told you this is not finished. We still have to give some counter information, and I mean we need. This is of course a recursive equation, so we need in some way a starting point. But the starting point doesn't have to be a known point. It has to be a random variable, meaning that we have to define. We can call it A1. So the mean of alpha at times alpha at times equal to 1, and the variance covariance matrix. So this is a matrix. This is the variance covariance of alpha 1 minus transposed. So this is the initial condition. So in order for this setup to be usable, I need to specify the condition at times equal to 1, which is, as I told you, it's not that we have to know where we were at times equal to 1. It's not necessary. We just need a random variable. And if you really don't know anything about the starting point, it doesn't really matter. You can put infinite variance. Infinite variance means I know nothing. So this is not really not a knowledge constraint. We can also express the fact that we have no knowledge about the starting point. And this is the so-called state space form. Sometimes they say state space model, but actually I call it just state space form because it's not a model. A model is something more than this. A model should know, in a model we should know what T looks like, how zeta looks like, Q, H, and so. This is a form where we can cast many, many models. And as we did, well, you already know linear regression, you already know because we just did it, ARIMA models. So the first thing I will show you we can cast into state space form is regression, linear regression, and ARIMA models. So let's start with regression. Linear. State space form, as I said. Well, it's simple. I mean, this looks already like a regression. So now y is scalar, epsilon is also scalar. With variance sigma epsilon. And that's it. Okay, this is time varying, and this has the regressors. This is actually a vector, or this is it's a matrix that is actually a row vector. Okay. So for example, if we have k regressors, this will be k times, 1 times k. This will be k times 1. And this is just okay, alpha will contain the regression coefficients. And if the regression coefficients don't evolve over time, well, then I just have an identity. This is equal to this. And of course, as I told you, if I know nothing about the value of the regressors, I can say, I give any arbitrary point, for example, I can give 0 and then say, okay, P1 is just a matrix that contains infinites on the diagonal and 0 otherwise. So you see, this is a regress process. This is the vector of the regressors. This is the coefficient of regression. This is the regression noise or error. And I'm telling that the coefficient, they just don't evolve. They just remain what they are. So actually, linear regression can be cast in before. And I don't know if you've ever been exposed to Bayesian statistics, but actually, the fact that I have to indicate the initial condition, this I can use as a called prior information. So if I have some information about the value of the regression coefficient, I can convey that information using here. I could put some numbers here. I put, of course, a variance which is more than infinite. In that case, the effect is that I'm shrinking the estimates towards my guess. Okay. This is like my initial guess. And if I don't put infinite variance, the smaller the variance, the stronger the shrinkage towards the initial vector. So it's nice because you could see it at both ends. Well, likelihood based, I haven't shown you how to build the likelihood function, but it's possible to build the likelihood function, and we'll see how. But anyway, this estimate of the alpha can be made in a maximal likelihood approach or using a Bayesian approach. And the two things are just almost the same. In one case, I put some prior information. In some case, I didn't put any prior information. Actually, for example, you've seen the ridge regression or not? Ridge regression is just regression where I shrink the parameters towards 0. Well, if I put some variance here, I'm shrinking towards 0 if I select ridge. And so I also get this ridge regression as a special case. The smaller the variance, the stronger the shrinkage. And really, if you want to shrink, you first have to standardize all your regressors, because then you usually you fix the same value for all the parameters to be shrunk. But for example, you did also in a neural network, it's called weight decay. It's the same thing. It's a ridge. It's a L2 regularization. If you want to call it without giving a specific L2, maybe. Yeah. Lasso is different because lasso is here we penalize by the square, the sum of the square of the coefficients, and lasso instead is the absolute value, so the sum of the absolute value of the coefficients. The lasso has some advantages because while a ridge just shrink towards 0, which when you have many dimensions is good usually because it's a form of reducing the complexity of the model. So, for example, neural networks are extremely parameterized models, so thousands of parameters, sometimes millions of parameters. There are too many. Even if you have a lot of observation, usually there are too many. So you have to find ways to make the model a little bit more rigid, and shrinking the coefficient towards 0 is one of the ways. And in neural networks, usually use this weight decay, which is a ridge or L2 regularization. If you use L1, so L1 is lasso. it does not only shrink towards 0, but it actually puts some of the coefficient exactly equal to 0. And indeed, lasso means one is shrinkage operator. So shrinkage and selection operator. And so that's SSO. So shrinkage and selection operator. And layer on list the absolute. List absolute. Sì, perché questo tu lo puoi vedere come una forma di shrinkage. Cioè, se al posto di mettere una varianza infinita, allora, prima di tutto suppone di standardizzare i regressori del tuo Z, così tutti hanno la stessa unità di misura. A quel punto io potrei dire il valore iniziale, conta che il valore iniziale poi influenza tutti i valori, perché qua c'è un'uguaglianza, non c'è un'evoluzione, rimane sempre uguale. Per cui tu stai dicendo il valore iniziale di alfa a media 0 e se metto una varianza finita, uguale, che ne so, a un lambda comune, perché tanto ho messo questo, tu stai dicendo, secondo me i coefficienti sono vicini a 0, secondo me. Poi adesso non vi ho ancora fatto vedere come si stima con la massima verosimiglianza. Quando vai a stimare la massima verosimiglianza, è ovvio che viene tenuto conto anche di queste informazioni. Ovviamente più hai dati, meno le informazioni importanti. Se hai pochi dati, invece questa informazione è molto importante. E quindi viene distorta la stima che sarebbe di massima verosimiglianza verso questa stima qui, che è una tua stima, diciamo, soggettiva. Quindi, che la puoi vedere come un reach. Si può far vedere che c'è un'equivalenza in questo caso. Chiaro? Lui diceva c'è anche il lasso, è vero il lasso, però qui noi supporremo gaussianità su tutto, ok? E la gaussianità vuol dire minimi quadrati, e per questo motivo sostanzialmente questo si trasforma in una ridge regression. Okay, another example, this time using some dynamics. So, just to complete this, in this example we have, okay, zeta t is actually a raw vector and it's equal to the transposal of the regressors vector. Then we have T, which is just the identity matrix. It's here, the T. We don't see it, but it's there. Okay. And then we have we have no errors, so actually we don't have R, and we don't have even Q, okay, because we don't have errors. Okay. We have H. H is just the scalar, which is the variance of the white noise epsilon. Okay. So if I have to, at the end of the day, when you define a state space form, you just to provide these matrices. So zeta, H, T, and R and Q. That's the definition of the state space form. Okay. And of course, the initial conditions, right? So A1 and P. When you provide that, you have the whole model. So let's go with something, as I told you, dynamic. Let's start with a simple model of the AR1, for example. Well, the AR1, it's very simple. We can define alpha t plus 1 equal to some phi t plus whatever eta. So this is scalar. And then my observation equation is just an identity. So you may say, okay, this is an autoregressive process. Why is there a t and not a t plus 1? It doesn't really matter. This is just a white noise. It's a sequence without linear memory, okay? So it doesn't really matter if I call it eta t or eta t, -1 plus 1 plus 5. Okay, it doesn't matter. It's just a white noise sequence. We use this form because this is the form that it's used in most softwares. Okay. Sometimes you have a form where the noise here eta is t plus 1. So it's the same as usually in, I would say, 95% of the software, it's this form it's used. So where you have t plus 1 on the left hand side and all t's on the right hand side. It's just a matter of taste. It doesn't really matter. So going back to our process, this is defining a AR1 process, clearly. Okay. And this is just an identity. We are saying, okay, the time series is an A1 process. What about the initial condition? When we have a stationary process, for example, suppose we have an AR1, which is stationary. What does stationary mean? It means that there is a mean of the process, or a long-term mean. And there is also a long-term variance of the process. Okay? So what about the initial condition? Well, if I know nothing, the worst I can say about a stationary process is that the mean is equal to the mean, and the variance is equal to the variance of the process. It's the worst I can say. Maybe I can say better, meaning that if I know better about the initial condition of the time series, I can have better information. But for a stationary process, the least I know is just the mean and the variance of the process. So in this case, this is, for example, a zero mean autoregressive process. I can complete the information. So this would be like eta is the white noise, variance sigma squared eta. So if you remember the variance of the AR1, okay, but the AR1 was very easy because we have already a vector AR1 in the state space form. What about the AR2, for example? How we can solve it? Because the AR2 is using two delays here. How can we get two delays inside the alpha vector? I mean, clue? Okay, remember, so the practice, this is the AR2 process. Well, the mean zero here. Well, I use eta, so we use the same symbols, but this is the white one. Okay, I'll show you a simple trick that actually we'll be using many, many times. Actually, this is the simplest way to write an ARMA model, or in this case, an autoregressive model in state space form. As I mentioned, there are many, many different ways to achieve the same goal. Some are more intuitive, some are less intuitive. Okay, so let's start with a very intuitive way. So we build actually a vector with two alphas. This is our T matrix. So we have I'll just write and then we will comment. And of course, the observation equation is very simple. So let's see what's going on. actually from the second line. What's the second line telling us? It's just telling, look, the second state variable is just equal to the first one, but lagged. It's the first leg of the first variable. So this is just the delay of this one. So when I go here, so this is one delay of the first lag variable, or the first state variable, and this is two lags of this variable. And indeed, we produce phi1 times the first lag, phi2 times the second lag. That's it. And of course, we put noise just on the autoregressive equation because the second one is just an identity. We are just telling second has to be equal to one lag. Okay. So this trick is the trick that we can use to produce many delays as we want of the state variable. Okay. Of course, the more delays, the longer the vector. I can, of course, produce a delay, say, I could produce the third variable that is a delay of the second variable, and so the two delays of the first one. So actually, this trick we can use to produce as many delays as we want of the state, or one of the state variables, okay? And so in general, for example, in general, well, let's think about a starting point here. Again, we have like, this is a zero mean autoregressive process. So the first one is an autoregressive process. The second is the delay of an autoregressive process. So it's the same autoregressive process. So I didn't put any intercept or nothing. So this is a zero mean process. So I can put as initial condition 0, 0 for the mean. And what about the covariance matrix? Suppose it's stationary, of course. Suppose it's a stationary autoregressive process. What's inside here? I'm not asking you the exact formula. I don't even remember the exact formulas. Well, I remember that for the variance, but I remember that of the autocovariance. So the first state variable is the AR2 process. So here I should put the variance of the AR2 process. Whatever it is, we call it gamma 0, okay? What about the second process? Well, the second process is again AR2 because it's just a delay, one lag of the AR2 process. So it's also a AR2 process. So the variance is the same because it's stationary. Even if I delay it, it's always the same. What about this? Well, this is the covariance between the autoregressive process and its first leg. Well, we call this order 1 autocovariance. So it's just this way. So we know actually if we know the parameters of the autoregressive process, we know everything about the initial condition because it's stationary. Okay. In stationary process, we can always use this information to initialize the process itself. Non è chiaro? Okay, so. No, ma non avere paura di fare domande che potrebbero essere insensate. Vuol dire che c'è qualcosa che non hai capito. Cioè? Dove? Ah, qui, ok, sì, te lo faccio. Sì, ma va benissimo. Siete voi che dovete dettarmi la velocità. Scrivo le cose. Allora, let's just substitute the equation. Let's just propose the equation like here. So the second equation is telling you the second state variable at times t plus 1 is equal to the first variable at times t, right? That's why it's written there. So at the end of the day, it's like, I change color. It's like if I'm writing, instead of this, I can write this. So this is just like writing, so this is equal to, and so this is equal to alpha 1 t minus 1. Okay, I'm just substituting the spec. So actually, this is telling you the alpha at t plus 1 is equal to phi times alpha at times t, so one leg, plus phi 2 times alpha t minus 1, so the second leg. Is that clear? So this is the second line, and the first line becomes, the first line is just saying you, let's make it first black. So the first line is just telling you this is equal to phi 1 times alpha 1 at times t plus phi 2 alpha 2. Okay, so this is just the same thing but written. Okay, and now I substitute. So I substitute this thing here, and here you have alpha t minus 1, alpha 1 t minus 1. Okay, because this implies, of course, alpha p 2 is equal to alpha 1 t minus 1. Okay, so it's like it's written this way. And of course, there's also the error. So the first equation has also this eta. Okay. Okay. And it doesn't matter. This usually you want the t plus 1 here. It's really not important. Okay. So, and this is an AR2, right? And that trick, I mean, get used to these tricks because we will be using that all the way. Okay. For example, let's try to define the AR tree, for example, autoregressive of order tree. Let's see how it works. Okay, so now we need 3 state variables. This is our T matrix. And here we have the same 3 state variables, but delayed. So this is a scalar. And again, here we will have, what we want to have is 1 delay, second delay, and third delay. How we can generate this delay? And we can. So let's start again from the third reason. So the third equation is telling you this, the third variable is equal to the second variable, but with a delay. Okay, I'm just reading the last line of this equation, right? So this, I'm reading. The second one is telling the second variable at times t plus 1 is equal to the first variable at times t. Okay. But then if I substitute this one into here, I can also write, so this is equal to alpha 1 t minus 1. So actually, alpha 3 is just 2 lags of alpha 1. Alpha 2 is 1 lag of alpha 1, and alpha 1 is 0 lag of alpha 1, of course. And you can go on and on. Actually, I try to already make you understand how they look like. You have the autoregressive coefficients in the first line. Then you have like an identity matrix starting from the second row, and here you have just zeros. And you can go on and on and produce delays of delays of delays on delays. It works this way. It's really, if you learn it once, then it's very intuitive. It's just repeating the same trick. Yes. And is this really useful? Yes, because as I told you, it's not very simple to write the exact likelihood function of an ARIMA model, because you need the likelihood function to provide maximal likelihood estimates. And we will see that the state space form will make the likelihood function of any model in state space form very easy to produce. And so usually the software, when you choose an L or CSS and an L, the function, whatever R or Python, will cast the model in state space form and estimate it using numerical maximum likelihood using the state space form. Okay. While when you select the conditional sum of square, you're not actually producing maximal likelihood estimates, but you're like producing like least square estimates based on some initial assumptions. Okay. So here, of course, they're asymptotically equivalent, but in finite samples, usually this maximal likelihood works better because you're using more information. That's the reason. What about the ARMA model? Let's try to. Another reason why this is useful is that sometimes when we do unobserved component models, one component could be also, I don't know, an autoregressive process. I mean, we're not excluding that word in an unobserved component model. So actually, we could have as part of a more general model, so some part of an autoregressive or ARMA model. Okay. So what about the ARMA model? Because okay, I showed you. Okay, there's a way to build the trick. This is also called, for example, the companion form of an autoregressive process, where you write like an ARP process as a vector AR1 process. This is an AR1 process, right? Because there's just one leg. So the so-called companion form is this object. Okay? Let's try with the ARMA 1.1. Actually, as I told you, there are many ways to do this. I'll just present maybe the one that I find more intuitive. So the ARMA 1.1 model is this one. Of course, sorry, I didn't give you the rest, but the rest is very simple. It's just zeta equal to 1, 0. Because this is the AR3 process, so we just need to select this equation of the state variable and say, okay, y is equal to alpha 1. So This is it. H is equal to 0 because we have no further noise. There's just one noise in the ARMA models. Okay. Okay. Well, let's just leave the one out. We don't need it. So this is the Varma 1.1. This is a little bit more tricky. It's not so intuitive, but it's not that hard. The idea is that actually we could see, in our case, we could see this in two ways. Actually, we can see an ARMA model as an autoregressive filter applied to a MA1 model, or as an MA filter applied to an autoregressive model. So just to be clear. So usually we write the ARMA model in this way. Minus. Okay. So I could see this object in two different ways. Because it's a scalar object, and so we can decide the ordering. So we can apply this filter first, and then apply this filter first. Or then we can apply this, or if you don't like the word filter, we can apply this operator first, and then apply this operator first. For example, suppose this is an autoregressive process with the same value, the same white noise. So this is an AR1 process, right? Okay, then of course I can write it using the symbols we now know this way, or this way. Okay, let's pass this process into a MA process. So let's define a new process. There is just an MA filter, so a moving average filter applied to this omega process or W process, whatever you want to call it. Okay, so you see, first I produce this W or omega process as an autoregressive process of order 1. Okay. And then after producing this process, I pass the process into an MA filter. So this is not a white noise. This omega is not a white noise. It's an AR1 process. What kind of process is going to be YT? Well, let's just substitute first with using the operators. Okay. And then instead of omega, let's write again the same expression using the operators. Okay, it's an ARMA 1.1, right? I'm just defining the ARMA. So what's the message here? I can build an ARMA PQ process in two ways. I can either first generate an MA process with those coefficients of the theta coefficients, and then pass that process into an autoregressive filter. So we can call this an autoregressive filter. Sorry, this is more now autoregressive filters, or I can do the other way around. I can build an autoregressive process and then pass that autoregressive process into a moving average filter. And in both ways, I will get the same ARMA process. Okay. So if you want to be even more concrete, we've seen we have in R we have this filter function. The filter function can produce autoregressive filters. It's called recursive filters, or it can produce moving average filter, and they're called convolution filters. Okay? There's just one filter function. Why is there not an ARMA function? Well, because you don't need an ARMA function. You just need to use that first using, I don't know, for example, the convolution filter, and that result, we apply a convolution filter to a white noise and get a moving average process. And then I apply the autoregressive filter or the recursive filter to the just built moving average process, and I have an ARMA process. Or the other way around, I can produce an autoregressive process applying the recursive filter to a white noise, and then I apply the moving average filter or the convolution filter to the autoregressive process that I just produced, and I have the ARMA. We can go in two ways around. This is this is something important because I got tricked once. When you move to multivariate Varma models, this is not more true because we can commute this because they're just colors. But if you have matrices, because of course when you go into var models or Varma models, these scalars they become matrices. And of course, the matrix product doesn't commute. In the matrix where I times B is not equal to B times A, okay? But in the scalar world, it's true. So we can, why am I describing that? Because the basic idea in one of the forms, the state space form of the Varma model, I can generate first the autoregressive process, just as we did in the purely R process, and then pass that into an NA filter. And for example, for the Varma 1.1 and for the ARMA 1.1, which is up here, so let's build. Here we will need actually two variables. Okay, we want to produce in this part here, we just want to produce a autoregressive process of order one. So actually this should be sufficient. The problem is that, remember that I need also one delay of that process because I have to pass that into an NA1 filter. So I need the autoregressive process, but I also need one delay of the same process because I want to use the MA1 filter. In the MA1 filter, I have the contemporaneous observation and the T-1 observation. Okay? So I need this and a delay. See? I'm sorry. So, first line is clearly a AR1 process, right? Because there's just the value of today is equal to phi times the value of yesterday, okay? And then there's a white noise, okay? The second object is just the delay of the first object, okay? So this is AR1, this is the same AR1, but lagged, right? As you see, this lag is not needed here. This is not an AR2 process. For the AR2 process, we would need this lag. For the AR1 process, we don't need that. But we need that for the next step where we want to apply the moving average filter. And the moving average filter we apply using the measurement equation. Okay, so this is the AR1, and this is the lagged AR1. So as I just showed you, if I pass an AR1 process into an MA1 filter, I get an ARMA1 blood process. And this is one way to get the job done. It's not the only one. This I usually call the horizontal representation. Why horizontal? Well, because to me, the NA part is horizontal. I just call it this way. I haven't found that name in no other place. Just to give a name to this representation. Because actually, as I told you, there are others. You may want to play and try to demonstrate. The next one I'm going to show you is also an ARMA 1-1. So in alternative, I can also define the ARMA process directly into the state equations. This is much less intuitive, but you can try to prove why this is actually a ARMA 1-1 process. Actually, we can try to prove it ourselves by substitution. So this is another representation for the same thing. This I call the vertical representation because now the MA part is vertical. Now okay, this is an AR1, so you don't see the direction. But now we would have like the autoregressive coefficient here, also vertical. And here we would have the identity measure. I'll show you the general shape later. But anyway, we can try to see if we can understand why this is actually working. Maybe we can start with the second equation. So the second equation is just telling us that alpha 2 is just a white noise multiplied by some constant, right? Right? This is 0, 0. So this is just the white noise multiplied by theta 1. What about the first one? The first one is equal to phi 1 that multiplies the delay of alpha plus there's the delay of this one here, okay? So this is theta eta t minus 1. And then, of course, there's the white noise multiplied by 1. Well, it's a 1, right? Again, the white noise has a different delay with respect how we are used to write it, but it's just a white noise. So if we name it eta t or eta t plus 1, it doesn't change its behavior. So this is a ARMA 1-1. It's clear. This is the autoregressive part, and this is the movement. So actually, this works as well. And this has an advantage with respect to the other one. And the advantage is that the whole process is built in the state variable. And so if we want to use it as a component of a more complex model, well, this is the way to go. If I want to add like ARMA 1.1, for example, components to a model where I have a trends and seasonality and so on, this approach is better because it's all included into the one state variable. So in general, what about, for example, the starting conditions? Well, the starting condition here are simple because, again, the starting condition for this form, we have an AR1 and the delay of the AR1. So they're exactly as the ones we saw for the pure AR1 form. The initial condition here are a little bit more, I mean, they're still, if it's stationary, they exist. And then there will be a moment in which I'll show you a general rule how to build initial condition, regardless of what kind of process is generated them as far as it's stationary. Here it's like, well, the second equation, the starting, well, this is mean zero, and the variance is actually the variance of this one times the square of this. And yeah, the covariance between the two can be computed. But anyway, I will give you a general rule to derive the initial condition for stationary process. Anyway, let's give you a general rule for building ARMA models. Okay, fix R equal to the max between P and Q plus 1. This R, so you have to take the larger between P and Q plus 1. This is going to be the size of your state vector, okay? So you already know the state vector will be R long, okay? So this is R times 1. So in the horizontal form, so this is like the horizontal. T is equal to phi 1, phi 2, up to phi R. As I told you, then we have like an identity matrix here. This will be R minus 1. And this will be all zeros. Okay. And then, of course, we have R is going to be equal to 1 and all zeros. Of course, if for example, P is smaller than R, then you just set all the p's that you have equal to 0. Is that clear? So, for example, if you have just an AR1 and you have a Q equal to 10, then you have, this is going to be 11 state vector, state variables, or you just have phi equal to 1 and all the other phi's that you can have, they will be just 0. And then the zeta is going to be just the M8 part. And the same holds for theta. If you don't have enough theta, then set them to 0. And so this is the horizontal representation of a ARMA PQ. The vertical representation is, so at the end of the day, we have just, this is the T matrix, This is the zeta matrix. This is the R matrix. And okay, the initial condition will be the stationary mean and the stationary variance and covariance matrix. For the vertical form, we have this. This time, the autoregressive coefficients are vertical. And then we have here an identity matrix of dimension R minus 1. And here we have all zeros. Okay. And here the R matrix is very important because we have all the theta coefficients. Okay. And zeta is just a selection, and we are selecting just the first statement. Okay. You find everything in the, I think there's maybe some typos or the indexes. You should look at the topology for some typos for the indexes. But anyway, this is just a general formulation of the R state space form. What about the integration? So the E. Okay, the E, usually when you work, when you do the estimates of R in a model, you first take the difference and then proceed this way. Okay, this is one way to proceed. Actually, we could even produce the integration within the state space form, which could be useful in some ways. Let's just do a simple example where we have, for example, we produce a ARMA 1,1, and then we have to do everything inside the state equation. So we use the second form, so the vertical form. And then you will see that we can use another trick to build the integration of the process. So the integration of the process is very simple. It's just saying, okay, the variable of today is equal to the variable of yesterday plus the thing that I want to integrate, which is also something we can write in this form. So for example, let's try to produce an ARIMA like 1, 1, 1. So first of all, let's just leave one place free here and just start here. So let's suppose like we are starting from the second state variable. Well, we can already write that, but we will start reasoning from the second one. So first, we concentrate on the second and the third one, which are just following the definition that we just gave. So according to our definition, for example, an ARMA 1,1 in vertical form, we have the phi here, we have 0 here, we have 1 here, 0 here, and then we have so if you look at I added another variable here, but if you don't look at the first variable, it's just like what we already see. It's a varma 1, 1 in the vertical form. So we have the phi 1, there's just one phi here, and then we have one theta here. So this is going to be a varma 1, 1 process, okay? We just proved that. This is going to be a varma 1, 1. We did the example. Now we want to integrate this, so we want this one to be the integration of this one. How we can build that? Well, it's very simple. It's just, I have to take the past of myself and add the process I want to integrate, which is that. So we already seen that alpha 2 is going to be in arma 1, 1. And what's the alpha 1? Well, alpha 1 is, if you just write down what's there, it's telling you, okay, alpha 1 is equal to itself lagged plus the arma 1 bound. And this operation is just an integration operation. So this is going to be an arima 1. Okay. So as I told you, you could actually take the difference of the original time series and just build an ARMA module for that. But actually, a nice thing, because in some ways it could be nicer to work this way, if I use the state space form, I can even impose the integration here. And of course, then I say the YT is just equal to the ARMA. So it would be just 1. And so I don't even have to transform, when I do the prediction, for example, I don't have to transform back the time series by integrating. It's all included already in the model. Okay. Oh, sorry, here's a 0. So this is just the operation of integration integrated into the state space form. Of course, if we wanted to put the seasonal integration, that's a little bit more tricky because we need many delays. For example, if we have 12 months, then we have to produce 12 delays of the variables in order to produce the integration. And that makes the state vector very big. And we don't want usually to have two big state vectors because computationally can become very heavy. But we could even implement the seasonal integration. But we will treat the seasonality in a different way, so it's really not a problem. Okay, that a lot of things to visualize and to learn. I guess so. But I can show you a web app that I built for you so that you can prove I mean, you can try to do your own exercises in putting ARIMA in state space form. And then check if you've wrote it the right way. So if you go into the material of streaming here, in the e-learning, so one of the apps is called SS Maker. Ta-da. So you have the horizontal form and the vertical form. You can select the order of the AR part, the MA part, and this will provide you the right state space. For example, if you want like a AR3, I don't know, MA2. So this is the horizontal form. So these are the matrices. And the only difference is that if you look at the vertical form, I'm not using the so-called R matrix because the R matrix I started using because of R, the language, okay? Because many other software, they don't have this extra R matrix. They have just the Q matrix of the variance covariance. So here, this is like R multiplied by Q multiplied R transposed. So that's why it looks this way. So let's go back here. Okay, this is R. And Q would be the variance covariance matrix of eta, which is actually a scalar, okay? And so the variance covariance matrix of the error would be R times Q times R transposed. And this is what I'm using here as a Q. So I define this to be Q. But of course, this is just 1 theta R, let's see. And then there's the same thing transposed. And then there is the Q, which is a scalar, okay? So if you compute that, you see that you get this thing here, okay? It's just the same thing. So this is, yeah, I implemented the whole Q and not R and Q separated, okay? Okay, and you can play around. I mean, this is kind of wrong. This is just like a holder. This is right if you use the horizontal representation is not right actually if you use this vertical representation. I should correct this. But anyway, it's more to symbolize that, okay, we can compute that it's stationary. And you can play around how much you want. And of course, we haven't seen the UCM yet, but that's also the part where I show you how to put the unobserved component models in state space form and so on. Okay, so you can kind of do your own exercise because you have a software that can check if your exercise is correct. Probably now you could pass your exercise to ChatGPT and would correct it for you. So this is kind of outdated now. Still, it's quick. Okay, any questions? Ok, dai, ci fermiamo qui. Vediamo sia i risultati della mia interrogazione a Leonardo per le aule, sia poi magari facciamo fare una votazione finale su quanti vogliono mantenere il venerdì e quanti il giovedì mattina e poi faccio una